Again, let's imagine we've got a mass sitting on a horizontal surface, like a mass on a table or something like that. And we know that there's a weight acting on it and a normal force. But now let's imagine that we start pushing this mass to the side. So we come over and we start applying a force pushing the mass to the side. So let's apply a pushing force. So push force there. Well, what's going to happen? Will the mass move or will the mass remain stationary? Well, that depends. It depends on how large the push force is. Let's take a look at an example of that. Here's an object resting on a horizontal surface, a book on a bench. And now let's imagine that we're going to apply a force. We're going to push on the book in that direction. Well, if I push very lightly with a small force, what happens? Well, the book remains stationary. If I push with a larger force, still the book remains stationary. If I increase my force more and more up, eventually the book starts to slide. But I have to keep applying a force to keep the book moving. If I stop the force, the book stops moving. So what's going on here? Well, there is some friction in between the bench and the book. But the value of that friction is a little peculiar because for a small force, a very small force, there must be a very small force of friction. For a slightly larger force, we must have a slightly larger force of friction. It's only when I actually push hard enough that I can actually get the book to start moving that we get a different kind of friction. Well, let's take a look at those. When we start pushing on the object for a small pushing force, what we find is that there is some other force acting on the object, keeping it in place. It must balance this pushing force, so it must be back in this direction. Where is it coming from? It's coming from the atoms and molecules at the bottom of the book and the top of the table kind of sticking to each other and keeping the book from moving. We call this force a frictional force. And when the book, or whatever the object is, whatever the object remains stationary, does not move, that is a particular kind of friction that we call static friction. And we will represent that with a lowercase f and then a subscript s. A lowercase f, lowercase s, subscript s. That is for static friction. What we noticed is that the static friction changes its value to match whatever the pushing force is. So if we apply a very, very small pushing force, the static frictional force will be very, very small. How do we know it's small? Because it can only just balance the pushing force. Because remember, we have F equals ma. And if the book does not move, if the object does not move, A is 0, the net force must be 0, which means whatever frictional force we have must just be balancing the pushing force. So small pushing force, small frictional force. Larger pushing force, larger frictional force. Larger, even larger, up until the book starts to move. So apparently, the static frictional force has a maximum value. It cannot just keep going higher and higher and higher. If the object is just resting on a surface, eventually it will start to slide. So Fs, the static frictional force, has a maximum value. We call that maximum value Fs max. So that's as large as the static frictional force can get, and it can get no larger. Well, what is Fs max? Fs max depends on a couple of things. First of all, it depends on the normal force. So remember, when an object is on a surface, there's going to be a force perpendicular to the surface. In this case, it's going to be exactly opposite the weight. Okay, but in general, that's not going to be true, so I'm not going to say it's always equal to it. But whatever the normal force is, Fs max depends on the normal force. All right, now, how is that? What do we mean by that? Let's go back to the book and take a look. Let's see if we can determine something about the maximum static frictional force. When I push on this book, I have to push at a force that's larger than Fs max to get the book to move. So I can get an idea of the value of Fs max by figuring out just how much I have to push before the book starts to move. Well, if I increase the normal force acting on the book, so by putting a mass up here, the normal force acting on the book from the table has increased. What I notice is that if I do this very, very carefully, I have to push a little bit harder to get the book to move. In other words, Fs max has increased. I could try this again by increasing the force a little more. I've got now 2 kilograms on the book. I try pushing on it, and I have to push a little bit harder. Could increase it a little bit more. Let's make this 3 kilograms. I have to push a little bit harder. 4 kilograms. I have to push a little bit harder. So what we notice is that by increasing the normal force, I'm increasing the amount I have to push to get the book to move. In other words, I'm increasing Fs max. Well, let's take a look at that. What we notice is that as we increase Fn, we increase Fs max. And we're going to make an approximation. We're going to actually say that these two are actually proportional to each other. Here's a little symbol I'm going to use occasionally. Typically it's kind of written like that, but to do it quickly I'm just going to draw it as a circle and then a little half circle. And this just means proportional to. So Fs max is proportional to the normal force. Well, we can actually make this as an equality if we put in a constant of proportionality. Now, what does that constant of proportionality depend on? Well, let me write it in here. This equals, and the constant that we will write is a lowercase Greek letter mu sub s. So this is a lowercase Greek letter mu. A capital mu looks like a capital M, but the way to draw this is it looks like a U, but with a tail in the front. So draw the tail and then just make a U. That is mu. And this is called mu sub s, and this is called the coefficient of static friction. With this proportionality of Fs max and Fn, mu s tells us how we can equate these two forces. Mu s basically tells us how much friction there is between the two surfaces. If we have two surfaces that are very slippery and slide very easily, then we don't need to apply much of a pushing force to get the object to move. In other words, Fs max will be small, and so we could even have a large normal force, so mu s would be small to give us a small Fs max. If we have two surfaces that are very sticky and do not slide very easily, then it would take a much larger force to get the object to move. Fs max would be large, and mu s would be large in that case, multiplying the normal force. So mu s basically tells us how much friction, how sticky are these two surfaces. Large mu s, that means there's a lot of friction between the two surfaces. A small mu s means they're very slippery. There's very little friction. Okay, very good. So that's Fs max. And what did we know? What did we notice? That Fs can increase from 0 up to a maximum value of Fs max. So what we'll write is, let me get rid of this here. What we'll write is that Fs can be 0 or greater than 0 all the way up to a value of Fs max. So the static frictional force will increase to balance whatever other forces are acting on the object to keep it stationary up to a point. It can only get up to a maximum value of Fs max, at which point whatever other forces there are, whatever pushing forces, overcome static friction, and the object starts to slide. When the object starts to slide, then a different kind of friction comes into play. We call that friction kinetic friction. Now let's take a look at kinetic friction. When we push hard enough to overcome the static frictional force, then we're working against kinetic friction. Some things that we notice, that if we push the book slowly, or if we push the book a little bit faster, it turns out that the force required to move the book at a constant speed are pretty close to each other. They don't change very much. Now, the fact is that if we increase the speed too much, eventually the frictional force does start to change. It does increase with the speed. But for low speeds, it turns out that the amount of frictional force, the amount of kinetic frictional force, does not depend on the speed. So we're going to make that approximation. We'll assume that the kinetic frictional force is independent of the speed of the book for now. We'll take a look at more complicated situations later on. But again, what we notice is that if we increase the normal force, it takes more kinetic frictional force to keep the book moving. Now, let me just mention, what am I doing? I am moving the book at a constant velocity. Remember, if it's moving at a constant velocity, what's the acceleration? The acceleration is 0. If the acceleration is 0, what is the net force acting on the book? It must be 0. So whatever force I'm applying must be exactly balanced by the force of kinetic friction. So when I'm pushing on the book at a constant speed, I am actually measuring what that force of kinetic friction is. Whatever I push is exactly being balanced by the kinetic frictional force. Okay, if we increase the normal force more and I push on it at a constant speed, oh, I have to push harder to do it with a larger normal force. Increase it more. Yep, have to push even harder. Increase it more. And yes, I notice I have to push it even harder. So we find that the kinetic frictional force also depends on the normal force. So let's take a look at that quantitatively. Now we'll assume that we are pushing on the book hard enough to have overcome Fs max, overcome the maximum value of static friction. But we're going to assume that we're pushing it at a constant velocity. Constant velocity means 0 acceleration. 0 acceleration means 0 net force. So we must have another force balancing our pushing force, and when the object is sliding, we call that the kinetic friction. And the symbol for kinetic friction will be a lowercase f sub k. And what we have found is that the kinetic frictional force is also proportional to the normal force. And for slow, small speeds, it is independent of the speed. So for now, we'll assume that it is exactly independent of the speed. And then we can make this an equality, again, by putting in a constant of proportionality. And that constant is mu sub k. That's a k. Where mu sub k is called the coefficient of kinetic friction. Okay, very good. An important point about the coefficients of static friction and coefficient of kinetic friction. Notice we could write that the coefficient of static friction is equal to the normal force divided by the value of Fs max, while the coefficient of kinetic friction is equal to the normal force divided by the kinetic frictional force. So what are the units of these two things? What are the units of mu sub s? Well, the units of mu sub s will be the units of the normal force, a force, so it's a Newton, divided by the units of the Fs max, static frictional force, the maximum value, which is a force, which will also have units of newtons, which turn out to be no units at all. So mu s is a unitless quantity. So that's an interesting result. There are no units that go along with the coefficient of static friction. Likewise, for the coefficient of kinetic friction, it's going to be the units of the normal force over the units of the kinetic frictional force. Again, newtons over newtons. The coefficient of kinetic friction will also be a unitless quantity. Okay, so that's very interesting, something to keep in mind. Let's take a look at some numerical examples of these forces. Let's stick some numbers in there.